Hello, welcome everybody to our webinar today, Standardless XRF Analysis. My name is Rainer Schramm, and I would like to talk today about the possibilities and limitations of using standardless method in X-ray fluorescence analysis. I think most of you who are working with XRF instruments have a software on board which is able to do standardless analysis. And the goal of my webinar today is to explain you a little bit better, to explain you more deeper how such a method is working and what are the limitations. Yeah, so that you have a better understanding on how you can use your XRF without performing an own calibration. First, we have to talk about the XRF measuring principle to understand why is it possible to calibrate an XRF and why you use it standardless. How does it work? So this is very important. Unfortunately, I have to go a bit deeper into mathematics to give you a basic understanding on how the mathematics will work and what are the consequences out of it. So what parameters you have to influence that your results still will be accurate. And yeah, last but not least, I will give you a few examples to show how the parameters you input into the software will influence the final results and where you have to be careful and you have to take care about. Okay, let's talk about some basics. So we would like to look into X-ray fluorescence analysis, and so we have to understand how this works. And the basics here is that if we have an atom and you irradiate it with X-rays, that then when we are lucky, one of the inner shell starts to ionize. That means an electron is leaving and an electron from a higher shell is filling up the gap. And depending on the element itself, there is a probability how much fluorescence is then created. We call this fluorescence yield. And basic rule is that as with low atomic number, the fluorescence yield is very little, and as higher the atomic number, it will increase. Yeah, so that we have then for high atomic number elements a very good sensitivity in XRF, and for light elements, so low atomic numbers, we have only very little sensitivity for fluorescence. Here another description. So it means that here we have the inner shell, which is also called K shell, and the next shell will be the L shell, and then the M shell. And if you create a gap by X-rays in the first shell, the K shell, the most inner shell, then it can be filled up either from the L, which you will then call K alpha lines, or it will be filled up by the M shell, and then we have K beta lines. The same here on the L shell. If it's filled up from different M shells, we call it either L alpha or L beta or L eta or LL. Yeah, so these are the ways how it works. And for example, a K spectrum looks like this. This is from iron K alpha and K beta. So you see that the probability that we create K alpha radiation is about 5 times higher than K beta radiation. Yeah? That means that this process happens much more often than this process. The same we have on the L radiation. That means here we have the L alpha and L beta with more or less the same probability, and the other two LL and L eta are of a less probability, and this you see here in that pattern. So L alpha, L beta are quite the same. The others are not so often happening. Yeah, and in this way, the spectrum is created. And so in the end, we want to do a calibration. That means we need to establish the relation between concentration and intensity. Yeah, this is what we have to do. And either we can do this by using standard samples, or we use by describing it in theory. And now I will display you the formula. This seems to be a bit complicated, but I will go step by step into it so that you will understand what is important for you, So you don't have to use this to calculate something. It's only now used for understanding. And you see that the concentration and the intensity is also in this formula. So that means this is the concentration of the element we are looking at, and this is the corresponding intensity. And with the formula, it is described how the relationship in between. And this formula is taken from a publication from Volker Thomson, who really made a good job to describe this kind of fundamental parameters, the theoretical description of X-ray fluorescence. And if you want to go a bit deeper into it, I really recommend you that article. The formula I'm displaying, it is of course simplified, so it only is valid for certain conditions. This is not really important today because I just want to explain you how it works from the principle. Okay, let's take this formula and we go now a bit deeper into it. So first, of course, we would like to analyze a sample, and we need an X-ray tube. And the X-ray tube will irradiate our sample with the intensity. This is this I0. So this you find here in the formula, and it's the excitation. And then this radiation goes, of course, into the sample. In the moment this radiation will penetrate the material, there is an absorption. And this is important. That means when radiation goes through something, it will be always absorbed by the material. The material here is your sample. So every element in your sample will absorb the excitation radiation, or the exciting radiation. And this is also what you see here as the mu from the sample. Then on all this part, when it goes into your sample, the element of interest, in our example iron, will be excited. How much? This is defined by the Q, and Q is, like I told you already, some transparencies before, is the fluorescence yield. So the fluorescence yield gives what is the probability that an element will be excited and fluorescence radiation will be produced. And this is, of course, depending on the concentration of the element. So as more iron atoms we have, as more fluorescence radiation we will create. And of course, it will be a part of the fluorescence yield. So how good can we excite iron? In the moment this radiation will be created, it has to leave the sample. So again, this will be absorbed on the way out. And this is also here indicated by this mu s based on the element. And then also we will have a path how deep the iron or the element of interest is analyzed in our sample. And this is quite important because there will be a depth where we can't see the iron anymore, because let us assume it will be excited here, and then on the way out, depending on your sample material, it could be absorbed 100%, so it will not leave. So there is a point in the sample where you can't look deeper into it. And this is always what we call this penetration depth. So how deep we can look into your sample. And this also will define, is your sample thick enough for the analysis, or will the intensity increase with increasing thickness of your sample? So these are very critical parameters. We have to talk more on the next slides. Then, of course, you have a detector which will observe your sample, but it can only look in a certain angle to it. And this is this part here. So this is the room angle. The detector watches your sample, and this means he will see only a part of the fluorescence radiation created, because this is sent out in all directions. But the detector can see only a part, and that is this room fraction he can see. Last but not least, we have here a part in the formula which is needed in the moment your sample is not thick enough, like I told you already. If you have a thick sample, that means it's really so thick that your X-ray can't go through, then this can be ignored. In the moment it is too thin, then you have to correct the intensity, because That means there's a concentration, but the intensity is smaller than it should be. And this is why then this has to be corrected. And last but not least, also very important as a definition of terms, sometimes we talk about fundamental parameters in XRF. And here the fundamental parameters is the mu. This is the mass absorption coefficient, and the Q here also including the fluorescence yield. These are values which are in tables, and your X-ray software is using it to calculate this formula. Yeah? And this is why we say we make an analysis with fundamental parameters. That means all the inter-element effects are not calibrated by standard samples. They are taken from tables. Okay, let's go further. We look a little bit about the sample thickness. And also here from Thompson, I took that slide here where he describes this function. So this exponential function depending on the sample thickness and the intensity. So you see how it works. That means the sample is getting thicker and thicker, and there will be a point where it's then infinitely thick, and the intensity will not increase anymore. While when we are on the other side, here we talk about a thin sample. Yeah? So here the intensity is directly depending on the thickness, and here in the middle we talk about an intermediate thick sample. Yeah? So these are the terminations we use in the terms we use in X-ray, and this is the explanation for it. Of course, the point is that if we analyze something with a standardless method, we have to talk about thickness. We have to think about, is my sample thick enough for this element of interest? And this we see here in the next slide. I made here a list of elements with increasing energy. And here different matrices, yeah, we are analyzing these elements in. And just take our example, iron. So if I analyze iron in graphite, or this would be also kind of a oil, for example, then my penetration depth is up to 4 millimeter. Is it a rock sample? It's 0.5 millimeter. Is it iron in iron metal? It's just 0.1 millimeter. And is it iron in lead? So very heavy matrix. It's just coming from the surface. So very important to know that if we look here on this graph, that we have to think about where we are. Yeah. So in this case, in the graphite, we can be here in an intermediate part, while here in the lead we are always thick. Yeah, because if the sample has more than 15 micrometer, it is called thick. Yeah, so we are already in this range. While graphite, you see, I can make a press pellet out of it. It's just 1 millimeter thick, and then I'm far away from my thick sample. And also, if people are analyzing heavy metals in, for example, plastics, like ROS application, then they would, for example, analyze lead. In a plastic sample, you see it's 1.5 centimeter is considered as a thick sample. And this could be that very often your polymer sample is much thinner. And then you have to take into account, how is this corrected? Yeah, how is the intensity made correct to take this into account? Okay, I'm just looking into the chat. There are some questions, someone wants to see. I will answer that in the end, these questions, so we don't lose too much time. So now I would like to summarize the theory. That means important for FP analysis is the sample thickness. And the sample thickness could be either defined by the user by input the mass, the diameter, and the density, or the thickness directly and the density. Yeah, this is needed to perform an accurate result of an unknown sample. And like I said, it depends on the atomic number, how thick is a sample. When is it called thick, and when it is still intermediate thick. Fluorescence yield is an important point. So the sensitivity increases with the atomic number. Then the exit depth, so how deep do we analyze the sample? And the matrix, that means for this absorption coefficient, we need to describe the sample completely. Yeah? Otherwise, it is not possible to make an accurate result. If we have some unknowns, not measured elements, then we cannot calculate the real result. I will give you some examples on the next slide for this. And we have the 100% rule. That means there is the possibility that you can leave one parameter open. We know this when we do few speeds, that we can let it calculate a loss on ignition, for example. We could calculate a dilution factor or an unknown matrix part, like, for example, the oxygen. But now let us discuss some examples. An easy way to do analysis is just a liquid in a cup. Yeah. So what do we have? We have a liquid which is in a sample cup, and then we need a film which covers the bottom. And so if we think about the path, the absorption for the ingoing X-rays and the outgoing X-rays, the film will absorb the X-rays. That is why it's important to define it, the thickness and the material. Yeah? You also have to define what is the atmosphere here. Normally we are measuring in vacuum. There is no absorption. But if we measure in helium, we have a small absorption for the very light elements. This is why it's important that you also define this. I give you an example now here of a measurement I did. Phosphorus in water. Yeah, and this is the intensity I got, 40,570 counts per second. And when I define the matrix, which the XRF of course cannot measure, so I as a user have to define this. And I say it's water, my result will be 1.41%. But if I define it as oil, the matrix, then I get only less than half of the value. So why? What is the reason for that? So the fundamental parameters, they look on the absorption of the X-rays going in and out. And in the moment I change the matrix, there will be a completely different sample matrix. That means while the hydrogen is the same in both, the oxygen and the carbon will be different. Oxygen is on the right of carbon in the periodic table. This means oxygen absorbs much more than carbon, and it absorbs a factor 2.5 more. This is what you see. That means a water matrix will absorb the phosphorus signal 2.5 times more than an oil matrix. And this is why our result is about 2.5 different. Yeah? This is the reason for it. We have exactly the same intensity, but if we look then in the formula and we want to calculate the concentration, the matrix will define the final result by the absorption. If I leave the film away, then you see that also this has a slight influence. It will also decrease the concentration because now we say that this intensity is just coming out without film absorption. Okay, different example. Let us again take a sample cup, but now we put a metal powder inside. It's a metal powder used for 3D printing, and it's stainless steel. And again, I have my cup, I have the film covering the bottom. So I have again my absorption of the film and an absorption of all the stainless steel elements coming out. And this will be the result I get first. So the first thing I will see is that my sum is not 100, but I measure every element. So what is the reason? Why do we have a gap here? And the reason is that, yeah, now we have a powder, and the powder contains particles. There will be some holes in between. So this is the first reason that we do not have a 100% filled volume. So this is why we can't reach 100%. The second point is that at every particle surface, the radiation ingoing and outgoing is scattered. So we lose scattering. We lose radiation by scattering. That means not all radiation coming in is used to make fluorescence, and not all fluorescence can be used to reach the detector. And this results in this gap that we do not analyze 100%, that we analyze only something between 80 and 90%. And if we go from a loose powder to a press pellet, it's not much better. Yeah, so it will go perhaps 5% up, but still we have the particles, and still we have the problem that we lose information by scattering. And this is one of the biggest drawbacks if we use our standardless method for powder samples, that we normally never reach 100% because there is information lost. And there's no way that our theory can describe this. Yeah? You can only cover this by empirical calibration, but not by standardless. So what can we do now? So one possibility is that we normalize it to 100%. Yeah? On the metal powder, when I analyze every element, this is allowed, this makes sense. And then if you compare it to a specs of stainless steel, you will see that it fits very well. And this is, for example, how handheld instruments are determining your material and tell you then the steel type in the result. Now, this is how it works finally by this trick that it's just normalized to 100%. So another example is polymers. So for example, you have such a hot pressed polymer, which can be measured under vacuum. The matrix is polyethylene, and you typically analyze these Ross elements. And also here, very important to know that these elements, brom, cadmium, mercury, and lead, they are really relevant to the thickness of the sample. Yeah? So such a sample like you see here with a few millimeters are not really thick enough for these elements. So you have to take care about the thickness of your sample. Okay, next example is again a polymer, but now I use 3D printed samples. So I had here the different filaments and all white, and I made pellets. And so the white color comes from titanium. So I made here an ash and a fuse bead to find out how much titanium is in these filaments. And now I analyze my pellets in the standardless software. And if I just define its polyethylene by ignoring the original materials, then you will see that the real value I determined by my wet chemistry and the standardless value is really different. Yeah. So because I defined a wrong matrix, it has nothing to do with the real matrix. But if I enter the real matrix into my standardless software, then I'm able to get more or less the wet chemistry value also by standardless. So you see how important it is that you define the non-measurable rest as precise as possible, and as better you can describe your sample, as better is your result. Okay, last but not least, I would give you some other parameters which are important on the example of a fuse bead. So it's a cement sample. We fused 1 gram cement and 8 gram flux, so lithium tetraborate and mixtures of metaborate. So this here was a mixture of 66 lithium tetraborate and 34 metaborate. And I just analyzed it by my standardless software, and I get a fantastic good result. But now I just enter a different flux, and you see what is the influence. Yeah. So going from the mixture to the pure tetraborate, you see already how it will influence my result, and you see how important it is again that you describe your matrix. And of course, what here is also taken into account, I didn't mention yet, is the dilution. So I have only 1 gram sample and 8 gram flux as dilution. And of course, I have to enter this, that the software is able to calculate this result only on the sample part. Yeah? Because the bead is, of course, the complete sample, where then the sample is only a part out of it. Yeah? So this is important to know. So the matrix, again, is important that you get a good result. Now another thing is I recalculated this by taking out the oxygen. So this is just the same analysis as element. So only calculated, converted from oxide to element. And the oxygen is here just put as a rest. And now what I did is that I recalculated in my standardless software this speed by ignoring the oxygen. I just say nothing about what is the rest. I just say make the elements, calculate the elements, and then you see how wrong it gets. Yeah. So then by just ignoring the unknown rest, my result really gets wrong. You see, we are about 5% different for the main components, and this is something where you even can't predict what the software is doing. And I would guess that every instrument software is reacting a bit different on this case, because you have here just a completely unknown rest. However, if you do it the proper way, that means, again, I say analyze this by elements. So this is the same table and this table. And I define that my rest is oxygen. So now I define it. Then you see you get in the end the same result than in the very beginning, because now the software knows, there is an unknown rest of oxygen. And you remember the 100% rule. So the formulas are able to calculate up to 100%. And now you see that you get more or less the same result than in the first case, where the oxygen was stoichiometrically bounded to every element and directly calculated and taken into account. Yeah. So these are the different ways. You see the parameters here: dilution, and defining of the rest, defining of the matrix, very important. And you see how the results going up and down in the way you do it right or not. So let me summarize the whole thing. So first of all, to use standardless software, you have to understand the principle of XRF. And very important, you have to know every parameter which is important, especially sample thickness, particle size effects, dilution, and defining the matrix in the right way. And all elements must be determined. This is also something I didn't mention yet. Of course, you can only describe the full sample if every element which can be analyzed is analyzed and taken into account. Okay, so far I thank you for listening, and I just want to announce that on our FLUXAMINA platform you will find more interesting courses, also I would really like if you come back to our next webinar. Now I'm open for your questions, and I will have a look into the list here I got. So first of all, the question is, can you explain again why we don't need calibration every time? So we don't need a calibration every time when we are analyzing an ideal sample. Ideal sample means that it's really homogeneous, that we have no particles. So we have a glass, we have an alloy, we have a polymer which was melted, we have a liquid. So in all these cases, we have no particles inside, and then we can think about an ideal sample, and then we can theoretically describe the whole XRF process, and this allows us to use this standardless software. And then we don't need an empirical calibration. The empirical calibration is always needed if one of the conditions I told you is not valid. So you have unknowns you don't know, you have particles and you don't know how they react to the result, then you need an empirical calibration. So then the paper reference, this was asked. I go back quickly so that you see that. Let me see here. Here it is. So now you can write it down. And then the next question is, for sample thickness of any organic sample, you should look at the first column. Absolutely correct. You can take this graphite column, and then you have a good indication how your K radiation is behaving on the thickness. And of course, if you go to L radiation, you have to look where it fits into the table. Then the question is, what standardless software is used? this is nothing special. This, what I told you, is valid for every standardless software. There is one thing I didn't mention in my presentation. This is the Compton correction. Compton correction can help to describe the unknown part, the unmeasurable part of your matrix. That means there the backscattering of the tube is used to get an idea of the complete absorption of your sample. And this can help, for example, to distinguish between water and oil or between different polymers, and is an additional information some of the standardless packages in the market are providing, but not all of them. Yeah? So next question, how do you define the best thin film? Does it depend on the sample or the XRF device? So thin film is always, has to be taken into account about thickness and material. So as thinner the film is, as more transparent is it for X-rays. And then we distinguish between polyester films like Mylar and polypropylene film. And polyester is absorbing more. So it's considered more thick. But of course, it has to be stable with the sample. So you always have to do a test. Does the film really last your sample? Does it leak? So this is always important, that you avoid any leakage, that you do not destroy your XRF device. Yeah. So you have to see what elements you're analyzing, how thick must the film be, and how good does your film last to the sample. There's another question. What if my samples are smaller than my sample mass? Yeah, this is also a condition which is very important to standardless software. That means if your sample do not fill the complete X-ray beam, then you lose also information. So this is the same then with the particles. And then also you will not get a 100% result. You will always analyze a part of your sample. And in this case, then, yeah, you have to check if you can normalize to 100%. Is this an option? For some samples like metals, this will be allowed, for others not. Yeah, so there you also have to be very, very careful. Another question here, is there a special way to evaluate a mixture of oxides and sulfide? Yeah, this is a very good thing. I think your question is in the way that when you say that you analyze something and you define the rest is oxidic or the rest is sulfidic. This is something which is very difficult to distinguish. I would say that the standardless software cannot distinguish between is your element linked to an oxygen, to an oxide, or is your element linked to a sulfide. There we can only go by experience that we know in a sulfidic ore, we have a mixture that some elements are present as sulfides and some elements are present as oxides, but this is just empiric. Yeah? So it can only be defined, and then you have to live with this definition. The standardless software cannot handle this in general. So there is, can you explain again the example of the polymer with titanium? Yeah, the idea of that slide was that I'm analyzing titanium in different polymers. And for the XRF, all the polymers are the same because we cannot measure it. And but in the real world, the polymers are all different and absorb the titanium result all different. And the quality of the titanium result is depending on how good I describe the matrix. And I have to enter it. I have to enter it into the software, and only then my titanium result will be correct. So another question, what matrix should I use when analyzing calcium, magnesium, phosphorus, and potassium in milk? Now I use water with different density. I think that makes sense, yeah, because the biggest part of your milk is water. And what I would do is that you play a little bit around with your matrix so that you add a bit organic to your water. And then you will see how the results are influenced. And then you need a standard sample to validate what you are doing. And in this way, you can find out what matrix really makes sense. What else do we have? Why heavier elements have larger depth penetration? Yeah, this is depending on the energy of the fluorescence radiation and how strong the radiation is absorbed by the other elements. And the rule is that as higher the energy, as lower is the absorption when it goes through the other elements. Yeah? And this is why heavier elements, we can see fluorescence radiation deeper and deeper into the sample. And this is why we penetrate more and more the sample. So it's an indirect effect. So then another question is minimum X-ray power to do standardless analysis. I would say this has nothing to do with the power. Yeah, the X-ray power is a product of the voltage and the current of your tube. The voltage will decide which elements are excited, and the current will decide how much intensity is coming out. And of course, this is also proportional to the time. So you can in this way influence the result. But we have to say, if you do standardless analysis, you need to make sure that all elements are excited. That is important. Otherwise, you will miss some elements. And then the basic rule that you have analyzed the complete sample is not valid. And in this way, then your standardless software is not working correct. Another question. What is your opinion on analyzing geological samples with standardless analysis? I would say this is the common way geological samples are analyzed. Yeah, like we do it in our lab. We have a program where we analyze the geological samples by press pellets and fuse beads, and both can be done with standardless analysis. And of course, you could fine-tune it by one or the other standard. This is done first-class analytics, but the standardless software really alone already gives fantastic results. Because if you have a full geological program with all these trace elements and majors, and you want to calibrate this with samples, you have a need of endless standard samples, and this is nearly not possible. Yeah, so you always will use the standardless software to help to analyze all different kinds of traces. Another question, can the sum of the elements for the cement program exceed 100%? I would say in a cement, this is nearly not possible, but we know this from other applications. For example, you have an iron ore, and you have the iron in a low oxidation state, like iron 2, and then during your fusion, it's oxidizing, then it adds up oxygen, so you can have in the end more than 100%, at least on the paper. In the real world, it's not possible. Yeah, but just by calculating from the elements to the oxides, it can happen that you have a sum more than 100%. The same will happen when you have calcium fluoride in a sample, and in the end you express your result as calcium oxide and calcium fluoride. Then the oxide is not there, but you express it as calcium oxide, so your sum will immediately go over 100. Yeah? But this is only a theoretical thing. It has nothing to do with the real world. So I think that is more or less all the questions here, and I'm so happy that you placed so many questions, because this gives me the feedback that it was an interesting webinar for you. And I thank you very much for all these questions. And if there is something left you still want to know, send me an email, and I'm always happy to answer your questions. And thank you very much for listening. And I'm very happy to see you in our next webinar again. Thank you very much. Bye-bye.